All right, welcome. Is everyone having a good re:Invent? Yeah? Is it day 3? Well, this is SEC227, Improving Security Through Modern Application Development. Thank you for coming. My name is Josh Dulac. I look after a team of security solution architects. Been with Amazon almost 10 years, based out of Dallas, Texas. I'm joined by my colleague, Gerardo Estaba, who's based out of Sydney, Principal Partner Solution Architect. We're excited to be here, excited to talk to you about application development. And in this session, we're going to look at and discuss why and how to improve security through modern application development. So let's define it first. What is modern application development? Well, it's an approach to designing, building, and managing applications that increases software delivery speed and improves the reliability, scalability, and security of your applications. There's a lot of benefits here, but particularly for this session, we're going to look at the security of modern application development. There's 3 key areas and some takeaways that we're going to look at today. First, we're going to look at the software release cycle and application security within that for the development of software. And then we'll look at infrastructure management and how that relates to the first. And then we'll look at some architectures for distributing applications and infrastructure security. Now, given by the title, this is 227. It's a 200-level session, so you can expect us to stay relatively high level. We're not going to be able to dive too deep because we have a lot of topics to cover. Right? So let's jump in. Let's look at software release and application security first. So in traditional application development, manual software release processes are fairly common. You'll have developers and operation teams, often operating in silos, that are manually building, testing, and deploying their software changes. Now, often, this manual interaction requires manual approvals and handoffs, making the process slow, error-prone, and relatively resource-intensive. When it comes to security, this requires more effort to identify potential issues, and the slower deployment also slows the ability to apply security fixes, leaving the application insecure for a longer period of time. I compare this to a more modern application development approach where we can orchestrate a lot of the development lifecycle through something called pipelines or CI/CD pipelines, which if you're not familiar, is called continuous integration, continuous deployment, and continuous delivery. But think of this as the orchestration engine to move software through a series of steps. And we can automate our software release through these pipelines using code pipeline or another mechanism to automatically build, test, and roll out code changes. Now, the benefit here is it speeds up not only the delivery, but it enforces consistency, thereby reducing human error and mistakes. Automation helps identify security issues before the deployments occur, and this reduces the risk of deploying insecure code into a production environment. And also another benefit is it enables quicker fixes and the ability to patch things if a security issue is detected later. Now going back to a traditional approach, security testing is often relegated to the end of the development lifecycle, perhaps just before a deployment. And usually this is a symptom of development teams or builder teams viewing security as an obstacle or a blocker. Security is friction. Sometimes it's good friction, sometimes there's too much friction, and teams will often push that back to the end or look for ways around it, right? And this behavior fosters a reactive culture that scrambles to fix problems only after they occur, and this can lead to delays, it can cause significant rework, much of your initial work is thrown away in order to rebuild something more securely. And finally, the lack of a unified proactive approach to security can result in inconsistent and ineffective security measures. Now compare this to more of a modern approach where you have the idea of shifting security left, which means moving it earlier in the process, even when you're beginning to code, right? And this allows development teams to identify and address security vulnerabilities much sooner than waiting till the end. Otherwise, the cost of mitigating threats or security issues actually goes up exponentially the later you find them in your software development lifecycle. Now, this earlier detection that you can implement earlier in this software lifecycle enables not only faster software releases and more secure releases, but it prevents that wasted development time and rework. And it reduces the cost of fixing those defects if they're discovered later. If you're discovering them in minutes and hours versus days or weeks, you can improve your efficiency and productivity. Now, it's not all just about tools and testing, though. It's also about people and a culture of ownership. Many customers we talk to tell us that scaling security knowledge has been a challenge for them, and we at AWS have dealt with that too. So here at AWS, we prioritize ownership. It's one of our leadership principles. We believe everyone is an owner of security. And if you look at the slides, on the left we have service teams, or builder teams, we'll sometimes call them. We have hundreds of these. And individually, they own the security of their own individual services. They are writing the code, they're building the software, they're deploying it, they're running it, they own it, they operate it, and they also are responsible for the security of it. On the right-hand side, we have a centralized security team that owns the security for the overall organization and simultaneously acts as an enabler back to the business. And we solve our scaling security challenge by distributing security ownership with a mechanism we call Security Guardian program. Now, in short, security guardians are trained security advocates within these existing builder teams. Other organizations and some of our customers will call them by various names, like security champions. You may have heard of Security Champion program, very similar. And we've spoken about this in the past and how we view this, the metrics that we track for it, the improvement and efficiency we've seen from it at other reInvent and Reinforce talks. So we won't dive into it too much today, but we'll provide a QR code at the end of the session and the key takeaways if you're interested in that topic and want to look at it for a full hour. But the point is that we can improve security along each step of the application development lifecycle, and we can use a number of tools and processes and automation to get security review feedback earlier. So we're going to look at each of these briefly and dive into just a few. But really, first, it starts with threat modeling on the far left there in the author phase, which is a great place for a security and guardian to get started between the builder teams and the centralized security team. Now, in that author phase, before even writing code, we can use threat modeling to identify risk and security issues. So threat modeling, if you're not familiar, helps you answer the question of what can go wrong. And that starts when you're defining what it is that you're building. When you get the requirements and begin designing the feature, you can then consider what can go wrong and design an appropriate solution to mitigate risk. Imagine the opposite. Imagine spending an entire sprint, maybe 2 weeks, building a feature that is insecure by design, and only finding out at the end that you have to start over. That'd be really painful to throw away 2 weeks worth of work, right? Fortunately, using threat modeling at the beginning can help you identify that, focus on the design, and reduce the likelihood that that will happen. If you've never done threat modeling before, we have a tool on our GitHub for our AWS Labs GitHub page called Threat Composer. It's a relatively simple tool. It's a lot better than trying to manage it yourself in a spreadsheet like I have. It can be somewhat painful. It's a great way to get started if you're not familiar with the process. Continuing to look at the author phase, this is where the developer works on a feature request or task, and developers are often being asked to write secure code, right? There's a few things that can help them with that, particularly training can help with that, knowledge sharing, experience. If you have a senior developer partnering with a junior developer, perhaps peer review during that process, that can help them write more secure code. Also, having local security checks within your IDE can certainly help. But what if you had something that helped you write secure code while you're actually writing it? Recently, we launched a tool called Code Whisper, which helps you write code faster and more securely. It's an AI-powered tool for developers, and it uses artificial intelligence to generate code suggestions in real time in your IDE. It can also provide actionable security findings as you're writing your code. And the way it does this is Code Whisper's security scan is integrated with Amazon Code Guru Security, which we're going to look at shortly. Moving from the author phase to the source phase, this is where you're checking in your source code, such as Python or Java files. And you might want to peer review your source code at this step, or you might be pulling in an existing artifact or open source code, right? This is where customers that I talk to are very concerned about checking in secrets, right? Passwords, tokens, API keys, access keys, that sort of thing. And they might use a tool like get secrets. You could use a pre-commit hook or an IDE plugin to detect whether or not you're checking in sensitive information into your repository. Or you can use it for scanning your entire repository, looking for passwords or access keys that might have been accidentally checked in, right? But you might also want to scan your source code or your repository for security issues beyond just sensitive data. This is where static analyzers, or other types of static analyzers, come in. Something called static application security testing, or SAST. And there are a number of various things that it can look for within source code. One thing you might want to consider or start with is OWASP Top 10, which is a set of issues for when you're developing web applications that you want to consider and mitigate risk for. Also, the common weakness enumeration Top 25. You might want to look for log injections or secrets, like we mentioned. And if you're using AWS APIs and SDKs in your source code or interacting with them, you want to make sure you're using them securely, right? There are many open source and partner tools that provide these capabilities. And Amazon Code Guru Security is a SaaS tool that also provides these capabilities. So we're going to look at that a bit more. So Amazon Code Guru Security is, like I mentioned, a static application security tool that uses machine learning to detect security policy violations and vulnerabilities, helping you to create and deploy secure, efficient applications. And it does this by using automated reasoning and AI/ML to reduce false positives. And the API-based design enables some flexibility so you can integrate it at various stages of your workflow or use it independently. One cool feature that I'm fond of is that the bug tracking capability will automatically detect code fixes and close the findings that are discovered without user intervention. So to help with the remediation, you're not left alone. Code Guru Security will also provide suggested remediation. So in this screenshot, I have some code here that's being flagged for using weak encryption. And at the top left, it describes the issue, but at the top right, it's providing a link to examples of compliant code. So rather than just being left to your own devices to figure out how to resolve that finding, it provides recommended fixes with example code. In terms of workflows and integrations, there's various ways that you can use Code Guru Security. You can directly interact with it by uploading source code in the AWS Management Console or in the AWS CLI. You might want to integrate it within your pipeline or GitLab or GitHub if you're using those. Or you can use it directly within your IDE using one of the available plugins. The workflow is pretty simple at that point. You just scan your source code, allow it to review and produce findings of potential security issues. And then you want to remediate those using the suggested remediations and let it automatically rescan and close out the bugs. All right. Moving from the source phase to the build phase, this is where you're compiling code, perhaps performing unit testing, style checking, or creating deployable artifacts or images. You can use something like code build or another tool to trigger these various tasks and checks that you define in a specification. And you can also do additional static application security testing here using other tools that maybe provide other types of checks. You can also consider using tools that provide more capabilities. You might want to analyze the software for potential known vulnerabilities, look at the software versions, for example. You might want to evaluate the software for known CVEs in open source or third-party components. You might want to produce a bill of materials, a software bill of materials that can be used by a centralized team for understanding the full landscape within your organization. And these scanners can be custom checks or partner checks or partner tools or even open source tools. One of the tools that we're going to look at today is Amazon Inspector. If you're not familiar with Amazon Inspector, essentially is a service that we offer that can detect software vulnerabilities and unintended network exposure in near real time for EC2 instances, Lambda functions, and container images that are stored in Amazon Elastic Container Registry, or ECR. Now, focusing on just the scanning function, Inspector can provide scans within Lambda functions and the layers within those functions, and for container images that are stored in Amazon ECR. Now, for Lambda, there's two types of scans. One is standard, and then that is scanning for application dependencies for known package vulnerabilities. But you can optionally enable code scanning, which scans custom application code in the layers and in the functions for code vulnerabilities. And that's provided by Amazon Inspector. On the right-hand side is container images stored in Amazon ECR. And there is a basic scan function provided by ECR itself that scans for known CVEs in OS packages. But you can optionally enable an enhanced scanning feature that scans for operating system and programming language vulnerabilities within the images. That is provided by Amazon Inspector. So the purple box there at the bottom right is provided by ECR, while the orange boxes are a feature provided by Amazon Inspector. Another feature Inspector offers is software bill of materials, or SBOMs. SBOMs can help you understand the components that make up your application, and then you can export that information into standard industry formats, including CycloneDX and SPDX. And first, you might want to just export this to better understand your current situation, and then you can use other tools to analyze or visualize your software supply chains. And this is where a centralized team or the builder team can begin to ask questions like, where do we use log4j, or where do we use specific versions of OpenSSL, right? All right, moving from the build phase to the test phase, this is where you're running integration tests with other systems, perform load testing, among others, and you begin to deploy this into environments, but not just one environment. There's potentially many environments here. Some customers have a dev, test, staging environments, for example. And many customers will also perform penetration testing here before they actually ship it to production and deploy. Right? And this is where dynamic application security testing comes into play. And the difference between dynamic application security testing and static application security testing is not just the name, but it's in order for it to be dynamic, it has to be running in an environment. You need to be interacting with it. Static analyzers are looking at the plain text source code, looking for potential vulnerabilities in the source code, while DAST, or dynamic application security tests, are actually interacting with it. You're sending packets to the machines or Lambda functions or containers in your environment and deducing whether or not there's a potential risk there. Right? So you could be crafting HTTP packets or HTTPS packets, checking the certificates that are running, things that can't appear necessarily in the source code. Finally, in the deploy phase, you can deploy to production environments. And we recommend to deploy small at first and then roll that out more broadly. And you can continuously monitor using some of the tools that we mentioned, like Inspector. And if something needs fixed, is detected, then you can use the same pipeline to push out a change in order to mitigate that risk. This is where kind of an operate phase comes in. Now that a builder team has deployed it, they should be expected to operate it as well. They are the owners of that software and owners of the pipeline for deploying it. And they can use continuous scans like Inspector to provide insight. So when a security issue is detected, they can push out updates and continue to improve the software and reduce the risk without touching production themselves. So in summary, the pipeline is where the people, the process, and the automation all come together. They're all orchestrated to shift security left and provide security checks throughout the lifecycle of the software development. But why stop here? Why not do this with infrastructure as well? And spoiler, the answer is that you can, and it's very similar. So I'll hand this over to Gerardo to explain more about that. Thank you.
Everybody. We're going to be covering security in infrastructure. And in modern application development, infrastructure is handled in a different way. And so it becomes like its own subject, right? We're going to continue talking about how to improve security with modern application development, and infrastructure plays an important part to it. So in many traditional environments, even in some that have still automated the software release process, they are still setting up the architecture manually. You can have engineers setting up servers and databases and networks following like a list of steps. Although this is less common than having manual software release, it still happens today. And as we know, with all things manual, it leads to increased errors, to inconsistency across the environments, and at the end of the day, longer development or longer times to deploy the infrastructure, right? Configure the infrastructure. From the security perspective, this inconsistency can lead to errors or misconfigurations that cause environments to be different, and maybe in some of those inconsistencies might cause it to be insecure. In contrast, in modern application development, we use infrastructure as code. Many of you will be familiar with it. It lets you as a builder to define the components of your application programmatically. And so the creation of your buckets, your Lambda functions, your containers, all of that is now written in code. And of course, similar to software, you have many benefits. Like you're using version control, and so you get repeatability. It makes the applications easier to scale and also to replicate the environments and making these environments more consistent because you replicate them from the same recipe. And it speeds up the infrastructure deployment largely. From the security perspective, infrastructure as code cuts down the risk of deploying misconfigurations that could end up in a vulnerability being exposed. And because it's just code, it means that you can apply the same security checks that you heard before on the software release cycle. And because you're getting consistent environments that look the same, then the effectiveness of those security checks become increased. It becomes more effective, right? And so many security benefits of treating infrastructure as code. And so the objective is that you're going to treat the infrastructure code in the same way that you or your team as developers treat the software code. So what we're going to do now is we're going to run through a similar pipeline of deployment, just focusing on the infrastructure components and what are the security checks that you can implement in them. And so let's start with the authoring phase. So here you can write or model your infrastructure using your infrastructure as code preferred tool. You can use AWS CloudFormation, of course. You can use Terraform. In my case, I'm going to start the example with one of my favorites, which is the AWS CDK, or the Cloud Development Kit. And the reason I like this is because it's using the normal languages that you use as a developer. So you can write it in Java, JavaScript, C#, TypeScript, and others. So this is an open source multi-language development framework that helps you model the infrastructure as code, similar to the other tools. Here you can see an example of a containerized application deployed on a Fargate. And what I like about this is written in C#, and what I like is that with only 20 lines of code, you're modeling about 500 lines of YAML that you would have to write in CloudFormation, and it's provisioning 50 resources for you. So it makes it very easy and very quick to model your application using your preferred language. So let's say we've written our application or our infrastructure. We've modeled our infrastructure using the AWS CDK. So we are in the author stage. And what it means is you can use some of the practices that you've heard before and the tools that you heard about before. So you can test for code security directly in your IDE using, for example, the Amazon Code Whisperer plugin or the Amazon Code Guru security extension or any other local IDE tools that you want to use. In the source stage is where you've chucked your CDK code into a repository. So here, similar to software, you can do peer reviewing. You can start with your static tests. In particular, you can use code security, like my colleague Josh covered. This integrates really well with GitLab GitHub, and obviously AWS code pipeline. But where it gets interesting for infrastructure is in the build stage. This is where you can extend your security checks to include the infrastructure configuration that's being modeled in your CDK application. And you do this with tools that are called policy validation tools. And you can see 3 on the screen. You can see CloudFormation Guard, you can see the Open Agent Policy, you can see CDK NAG. I'm going to run you through one of those as an example. CloudFormation Guard. So it is an open source CLI that helps you do 2 things. First, you express your policy as code, meaning that you define what good looks like, what's allowed, what's not allowed. And then when you are creating your CDK applications, you have a validation process where you validate that what you've written complies with the policy that you've created. So you define the policy, and you use the policy to validate. And this is something that you can use at synthesis time in your build phase. So this is what it looks like for CDK. For CDK, you can use the CDK Validator CFN Guard plugin, because CloudFormation Guard works for the normal CloudFormation in YAML or JSON, but you need this plugin for CDK. And what you do is you add it to your application with a couple lines of code, and then you can either disable the default rules that it comes with, because it comes with a set of rules that are actually inherited from a list of protective controls in Control Tower. You can disable the ones that you don't like, and you can bring your own rule as well with a couple lines of code. Very easy. So I've defined my policy, and what you do next is when you are creating your CDK apps, a single CLI command, CDK synth, will generate a report after evaluating if your CDK application complies with your policy. If it doesn't, you're going to get some details about why. For example, you see that a bucket, a single bucket, is not encrypted as it should with a KMS CMK key. And this is a subset of the report. If you go further down, you're going to see more details about what bucket was it and help you mitigate it. So you can see that this is something very easy, and it's an opportunity for a lot of you that have already adopted infrastructure as code, maybe a long time ago. This is a way for you to introduce security checks into the infrastructure configuration of your pipelines, right? Very powerful. The rest of them are similar in that you define a policy, and then during deployment time, you run a validation against the policy, right? You're shifting left the checking of these security issues for infrastructure as early as possible into the deployment lifecycle. When it comes to test, this is where you start making, you're testing your application in its running state. And my colleague already covered Amazon Inspector and how it can help you scan for vulnerabilities in your instances, in your containers, in your Lambda functions. But I'm going to give you one more tip related to infrastructure, and it's the AWS IAM Access Analyzer. With this tool, you can automatically run security checks for your IAM policies and alert you if some risky IAM policies are present. For example, if there's public access for buckets or if something is not encrypted, and as part of your infrastructure deployment, you can fail the deployment if one of these risks are alerted by AWS IAM Access Analyzer. And finally, on the deploy stage, there's something interesting here you can do as well for infrastructure, and is you can test for configuration drift. And there are 2 main ways you can do that on AWS. And you can see how that's important, right? If you, let's say that your CDK app went all the way through to being deployed based on a configuration that it had initially, but then something happened along the way and your configuration has changed a month later, you can see that could open some unnecessary risks. So 2 tools you can use for this. AWS config rules is a way to automatically evaluate that your AWS resources are configured based on your desired policies and your desired states. If some configurations deviate from what you want, config rules can actually either alert you or even better, auto-remediate. And so the time that you are exposing your applications or taking risks is actually reduced if you automate this. And the second one is with CloudFormation drift detection, which detects when the configuration of your CloudFormation stacks changes. You can get an alert on this and act accordingly. And one last thing that I have to mention, because we're talking about infrastructure that's been deployed, and is Amazon Guard Duty, which is our service for continuous monitoring and threat detection that uses machine learning to alert you on any security issues. So very useful for the infrastructure side of things as well. And so there you go. By treating infrastructure as code, not only you're getting all the benefits of the modern application development in that the deployments are going to be more consistent and faster, but you can also leverage the opportunity of bringing those security checks left to make sure that you're detecting the security issues early and getting confidence as your application moves towards deployment and production. Okay, the last topic for today, we're going to talk about distributed applications and infrastructure security. There are a lot of things that we will discuss related to improving security, and some that are challenging and how to deal with that challenge of the distributed applications. We'll get to that in a minute. So in traditional software development, it is very common for large and complex code bases to grow over time, sometimes decades, sometimes by multiple generations of developers, hundreds of developers that contributed to this thing that became very big. And this is what's sometimes called a spaghetti code, which is a mix of all libraries, tangled dependencies, redundant functionalities, something that is very complex for anyone to understand. Now, this complexity makes it hard to update the software, right? And so as a result, it slows down software release, it slows down innovation, and it increases cost because you have to spend a lot more engineering time to build or to change anything in that spaghetti code. Now, from the security perspective, these code bases are also risky, mainly because they can make it really hard to identify, first, any vulnerabilities or issues, and second, to actually deploy the changes without impacting the rest of the processes within that code base. In modern applications, we focus on sometimes componentizing software or reducing the size of these software components into smaller, distributed, and independent components that are responsible for individual functions, right? Individual pieces of business logic. Doing it this way has many benefits from the software process perspective, like applications are easier to scale because it means you can scale each of the components independently. It also improves fault isolation because if one of those components fail, potentially the others haven't, and so you're less likely to have like a full-blown outage. And at the end of the day, it speeds up development since the teams can work simultaneously on different components and update them simultaneously. Very different to having a spaghetti code. And when it comes from security, these componentized softwares allow you to limit the scope and the permissions that you give each of the components. So you can think about the risk profiles of each of the components and target your permissions specifically just to them. And because it's also making it easy to identify issues, because your components are a lot smaller, it results in faster response when there's a security event or a new vulnerability that's been discovered. And so when you want to architect for componentized software, it naturally is going to lead you to distributed applications and very often microservices. So I'm going to very quickly talk about microservices. We see this as not only a way of architecting your applications, but also as an organizational approach. So the way that teams organize around software development being composed of small and independent services that communicate over well-defined APIs. And while microservices is one example of a distributed application that makes it easy to scale and faster to develop, they can introduce complexity in terms of service discovery, load balancing, network communication. And you'll hear about one of those complexities in the security side in a second. So I want to contrast distributed applications and to traditional, let's say, applications, where you may have, let's say, a single code base, single database, single network entry. In principle, that sounds a lot simpler to secure. But the problem with these applications is that there's an overemphasis on that perimeter, focusing on firewalling, focusing on intrusion detection systems. And this approach neglects the different components of the application and the other layers, like, for example, the data layer. Obviously, I'm making a generalization here, but when you are too focused on the perimeter security, you can potentially have little to no resistance when there's a breach through that perimeter, or when you have an insider attack or an insider risk, right? And another issue with this is that you tend to apply security rules uniformly, right? So you get one big brush of security across all of your application, and that lacks the nuance and the specificity that's needed with applications that are more complex and comprised for different services with different risk profiles, right? With microservices, or in modern application development, we want to apply security at all layers. This is sometimes called or referred as defense in depth. And this approach, what it's doing is integrating security into every component of your application, into each one of those services, into the data services, and of course, into the network. And one of the benefits is that this multi-layer approach gives you redundancy. If there's an issue with one of the layers, hopefully, the others are still there, and you're less likely to have a full-blown security event. And second, and this is for better or worse, it lets you be more precise with your security controls. And the reason I say it's for better or worse is you could see how this could be a challenge in distributed applications where you have multiple components and multiple services. So what we're going to do in the rest of this session is we're going to take an example microservices architecture, and we're going to run through how to apply security at multiple layers into this distributed application. So let's come up with one. Let's say that you have a lot of API services that are fronted. These are microservices fronted by an API, and they're routed through those paths. So we're going to be using Amazon API Gateway, and we're going to be creating API resources to represent those individual paths. When it comes to compute, in modern applications, you can generally choose among having a containerized application with, let's say, ECS or EKS, or you can choose for your application to build serverless, and you choose AWS Lambda. One great benefit of microservices and distributed applications is you can give each team the freedom to choose their platform of choice depending on that particular, the needs of that particular service. So that's why you're seeing both containers and Lambda in this architecture. However, for the purpose of securing our application and make it a bit simpler, I'm going to stick to serverless for our example. And then you have the data side. Some microservices have their own data store, or it's very common, a very common architectural pattern for the microservices to have their own data store. So in this case, let's say that we have a couple of those services that are requiring for key value stores, so we choose Amazon DynamoDB for it. And some other microservices require a relational database. We're going to be using Amazon Aurora. So this is what our simplified architecture is looking like in terms of AWS components. And let's add one more thing. Let's add maybe that we have a single page app written in React, stored in Amazon S3, and delivered to users via Amazon CloudFront. So let's start securing this thing and applying multiple layers to it. Where can we start? Maybe we start with credentials. Let's say that you have users accessing and logging into or authenticating in your application. Where can you store user credentials? Well, of course, the answer is definitely not on the database. Doing your own storage of credentials with the mechanisms for encrypting and encrypting and also handling the authentication flows, this is something that you shouldn't do unless you're in the business of identity. But for most of us, you should be relying on a standards-based, maybe an OpenID compliant, centralized identity providers, such as the ones offered by Okta, by Ping, by Auth0, and of course, Amazon Cognito. So Cognito offers a user directory that can scale to millions of users, and it handles authentication for you. So by choosing Cognito, you're making the application more secure because you're leveraging the in the shared responsibility model, you are offloading some of that responsibility to Amazon in the case of Cognito, or to your OpenID provider if you choose another one. So let's move on from identity to Amazon API Gateway. So securing API access is very important because this is usually the entry point to our microservices. So Amazon API Gateway has several ways of actually controlling access control. I'm going to run you through two of the most common ones. The easiest one is the native integration with Cognito. So the user authenticates against Cognito and then receives a token. The token is inspected by Amazon API Gateway and make the decision whether the call is going to be allowed or not. The second option, which is also very common, is if you're using SAML or you're going to use another better token authentication technology, or such as, for example, using an OpenID provider, you can use a Lambda authorizer. So with a Lambda, the decision is made right in your own logic, and you can do that by inspecting the tokens within the Lambda function. And then the calls are allowed or denied in a similar way. You have more work to do here because you write your own logic, but the result is the same. So that's access control for API Gateway. But there's something else we can do with APIs. Because another important security principle is to never trust user input. And Amazon API Gateway can help you with that with some basic request validations. So you can check for things like parameters and query strings and headers. You can also make sure that the payload complies with whatever JSON schema request model that you configure for your method. So whilst these are some basic request validations, they offload you as a builder and as a developer to include those in your application, and it means that you are checking that earlier before actually hitting your application. And a third and last protection that you can implement in Amazon API Gateway is with a very common vulnerability with CORS. So CORS is a security measure that needs to be applied or implemented in some APIs to let web browsers access them. So you can restrict what headers, what methods, and what's the origin domain that's allowed for our applications in Amazon API Gateway, so you don't have to do it as part of your application. Again, shifting left this functionality. So we've added 3 security methods or mechanisms to secure API access, right? Access control, request validations, and CORS. So let's move to another layer in our application. Let's go to DynamoDB. So access control in DynamoDB is handled by IAM, right? So here you have an example of a policy where you are allowing the action of getting an item to a single table that's called inventory table. So you can see that we've scoped down not only the actions, but we've also scoped down the resource that this policy allows access to. But is there a way in IAM policies to further scope down to maybe the user level? And this is where it gets very interesting, because one of my favorite parts of IAM is this conditions section. So this is an example, but this is relying on a native integration between Cognito, Dynamo, and IAM. So the leading keys condition here represents the partition key of that DynamoDB table, that first attribute in the table. And what we're saying with this condition is, if the leading keys matches, or no, if the Cognito identity of the requester, so if the Cognito identity of the requester matches the leading keys of the item, it can be allowed. What this means is now the user's own identity has become the boundary of what items they can access on a table. Very powerful. You didn't have to write a single line of code. This is all native integration. But the recommendation here is, not only for Dynamo, is make sure that you check those conditions in IAM, because they help you further scope down the permissions in your services. So let's move on to S3. How do we secure Amazon S3? So by default, let me say this, all Amazon S3 resources, objects, buckets, and related sub-resources are private by default. Only the owner that created them on the AWS account that they created them on is the one that can access it, right? Similar to DynamoDB, this is done through IAM, through a resource policy, which for buckets, they have another name, just because, sometimes called bucket policies. Both names are valid. And what you do here is you specify how your bucket can be accessed. In our example architecture, we had a bucket with a single page React app being accessed by CloudFront. So one of the things that we want to do here is we want to restrict that the access to our bucket can only be done through CloudFront. And you can do it with this example. So in CloudFront, you can create an origin access identity, or OAI. And you can give this OAI permission to read the bucket. So very simple, and it's guaranteeing that the only way to access this bucket will be through this particular CloudFront origin access identity. Let's move on to Lambda. So Lambda has, the permissions in Lambda has two main sides. On one side is the resource policy for Lambda, similar to DynamoDB, similar to S3. They define who can interact with the Lambda. And so Lambda can be triggered by a few dozen different services. And so you define in this policy who can actually trigger Lambda. The second side here is what are the actions that our Lambda function can do? And you can do that with the access policy. So even if you write code within that Lambda to interact with, say, an S3 bucket, if you don't have a policy, an access policy that allows this Lambda to interact with the bucket, then this call will fail. And there's an additional policy here, and it's the trust policy. And this is something that gives your Lambda function permission to assume that the role for that access policy. So there are two sides to it. What can interact with my Lambda? What my Lambda can interact with? And in what my Lambda can interact with, also, how do I let this Lambda assume that role? And you do that with a trust policy. All right, let's move on to some of the common issues to solve for in terms of security for this sort of applications. So we've covered cores, which is a common one, but there are others on the screen. Distributed denial of service attacks, cross-site scripting, and SQL injection attacks. So let's address the first one first. DDoS, or distributed denial of service, is a malicious attempt to overwhelm your resources, to disrupt the normal traffic of your resources. And attackers can target APIs or Route 53, your DNS. They can also target your CloudFront distributions. So one of the first best practices that we can implement here is we don't have to expose our APIs to the public if we don't have to, right? Instead, we can enforce that all the access to our APIs is done by CloudFront. That gives us one less attack surface to worry about. And so you're left with Route 53 or with your DNS, and also with CloudFront. So some good news. All AWS customers benefit from the automatic protections of AWS Shield standard by default in all AWS regions at no additional cost. So AWS Shield standard is for DDoS protection, but it's only focusing on common network and transport layer DDoS attacks, such things like SYN floods, UDP floods, and some of those other reflection attacks. For more sophisticated protection, such as for application-level DDoS attacks, you'll have to enable Shield Advanced. And this will protect you for things like HTTP floods, and it will even give you access to a DDoS response team that can apply further mitigations in case you are ever under attack. So this is a simple one. It's not simple when you are under one of these events, but the mitigations are simpler for you to get some protection, right? The other two, the cross-site scripting and SQL injection, are two of the most common OWASP risks to web applications. Cross-site scripting, to put it in simple words, is sort of like tricking a website into displaying harmful content from a third party. And a SQL injection attack is sort of like sending hidden SQL commands into your database inadvertently. So basically generating unwanted actions in your database. And although if you're doing modern application development, most modern application development frameworks these days can have their built-in protection, as developers and as builders, we're still responsible for validating the user input. And so how can AWS help with this and shift that to left? And it's through the AWS Web Application Firewall. So AWS WAF is very simple to use. You can create an access control list, and then you attach rules to that access control list. There are some managed rules that we offer you, and you can just pick them. In this example, I've picked 4 managed rules. One filters based on the region the traffic is coming from. Number 2 and number 4 are the two that cover the 2 attacks that I've just talked about. And there's a third one there, the size, and this is one that's checking for the payload size, which is always nice to have if you know that any genuine traffic shouldn't have more than 1 kilobyte. But with WAF, you can also write your own custom rules and add them to the firewall. Okay, so we are stopping these attacks closer to the users before ever getting into our application through the use of WAF. But there is something else. What if that SQL injection attack is not coming from the outside? What if it's coming from the inside? This could be a mistake. It could be an intentional mistake, but it could happen. And so if we are running microservices, serverless microservices in Lambda, how can we prevent this attack from happening? Well, you're certainly not going to put a WAF in front of Lambda, after Lambda. But you can, and this is a best practice, use prepared SQL statements. So you do this by parameterizing the queries so that Lambda is forced to use a single input. This is an example of how to do it in Java, but it's something that you need to make sure that you incorporate into development practices, that you are parameterizing these queries. Okay. The last component in our architecture is relational databases. So let's talk very briefly about how to make sure that we're securing access to our relational databases, right? So normally, with relational databases, you make a network connection over a port. In the case of MySQL, it's 3306. And then as part of this call, you need to embed in your connection strings a username and a password. So if your application is running in Lambda, how can your application access this username and this password? Well, there are several ways you can do it. You can, of course, hard code them because it's easy. But we know that secrets in code is not a good idea. You can accidentally publish them to a repository for all your team to see, or even worse, for all the world to see, if you publish that to a public repository. So please don't. Another two options is with environment variables. Lambda allows or supports environment variables being passed to it. Meaning that you can programmatically pass this username and this password. Or alternatively, you could pull a file, let's say from S3. You give a Lambda permission to access a bucket, and you pull that file from S3. This works, certainly better than hard coding them, but you're going to have to spend some engineering cycles in building the mechanisms for encrypting that information and for securely accessing and retrieving them. So it can work, it can be secure, but my argument is that you shouldn't be building the mechanisms around it. So instead, you should be using a secrets manager. The reason for a secrets manager is, or the main reason, it provides both the simplicity and the security. So if you're using, for example, AWS Secrets Manager, it's going to store the credentials securely for you. It's going to give you an SDK to retrieve the credentials, meaning that you don't have to think about the mechanisms for retrieving credentials or how to encrypt or decrypt these credentials. And third, very importantly, it can rotate the credentials for you, which is very secure. It makes applications more secure, because we know by this point that temporary credentials are better than permanent ones. And this can work on RDS, on Redshift, and on DynamoDB without impacting the availability of your applications. So a service like AWS Secrets Manager actually simplifies your life a lot, and it enforces this secure handling of credentials. And this is not only for databases, it could be for any type of secret. Now, in all these cases, we're using that username and password for the database. And that's not always a great idea. I mean, yes, it's the way that the relational databases work, but you can see how everyone using the same credential is not necessarily enforcing least privilege, right? And so, is there another way? And the answer is yes. So you can authenticate with RDS and receive, with IAM, and then you receive a token for that is valid for 15 minutes that allows you to access your RDS instance. So this is what we call IAM authentication for RDS, and is also secure. If you rotate the passwords with Secrets Manager every 15 minutes, then you're not getting additional benefit in that regard. But this is a way to create an abstraction and disable username and password access completely from your relational database. Pretty cool, hey? So these are the two. Many ways to access your database. Some insecure, some secure but require some work, and the two that are simple and secure. Please do the last two. So look at all the security layers that we've applied to our microservices architecture. So clearly, this is one of those things that is going to result in a more secure environment, but it is not necessarily simpler to secure, because there are more components, there are more nuances to it. But the benefit of doing that is you're implementing redundant controls that can, in more precise permissions, that at the end of the day are going to make your applications and your infrastructure more secure. OK. And so here's a summary of the 5 practices that we talked about for traditional development and modern application development. These are, of course, generalizations. And this session being level 200, we sort of covered a lot of topics, not in a very deep way. But the important thing to remember here is you can consider the general principles of the 2 types of doing these things and assess how your own team can benefit from making a few changes. And on the modern application development side, we covered a lot of security benefits that you can get from it. When you detect the issues earlier, you can respond to them faster. You can prevent misconfigurations that end up in insecure environments, and you can be more targeted in enforcing the security measures. In terms of tooling, we covered a lot between Josh and I. But if you go back, I want you to consider the 5 that are here. Code Whisperer for implementing the security checks in your IDE, Code Guru for those static tests, CloudFormation Guard or another policy validation tool, Amazon Inspector for your automated vulnerability checks for EC2 instances and Lambda and container. And finally, IAM Access Analyzer for security, for verifying the risky IAM permissions. There are some resources here. I'm going to leave this slide on for a few seconds if you want to take a picture. And while you do that, I'll tell you, we're a data-driven company, and we really appreciate your feedback. So please don't forget to go into your app and rate the session and tell us what you like, what you didn't like. Thank you very much. If you want to have a chat, my colleague and I are going to be outside because the next session is coming up. Enjoy the rest of reInvent.